So we're going to finish up this a little bit by talking about what makes materials into magnetic materials. We've explored how currents make magnetic fields, but remember that compasses are a much older technology than currents. How does a permanent magnet create its field? And it comes down to the atomic structure of the magnet. Some materials, such as iron, nickel, or cobalt, exhibit significant magnetism and can be magnetized. That is, made into take an unmagnetized piece of iron and make it into a magnet. You do this by striking it the same direction or bringing a very strong magnet nearby. Such magnets are called ferromagnets, from the Latin for iron, and the phenomenon is called ferromagnetism. Ferromagnets align strongly to external fields. Other materials will align, although weakly, exhibiting a weak magnetic field in the presence of an external field. These are called paramagnets, and the phenomenon is called paramagnetism, para for align or with. When the external field is removed, the paramagnetic field also vanishes. And then all materials, for quantum mechanical reasons, will exert a weak field opposite to an external field. When that's the only response, the material is called diamagnetic, for across. What's going on? Well, every electron, like all subatomic particles, possesses its own dipole magnetic moment, which we usually represent as sort of a line pointing in the direction that a tiny little compass with the electron would go. So you have the electron, and we say that it's got some moment. People used to think that this came from the fact that it's a ball of charge that is spinning, and a spinning ball of charge would be some kind of current and would produce a certain magnetic field that comes out of it. That's a very classical approach, and we don't really think that's the case anymore. We really think that at the root level, electrons just possess magnetic moments. So do protons, so do neutrons, so do quarks. They're just written into what makes an electron. If you try to make it work by saying, oh, the electron's a thing that spins, you find out that the spinning has to happen far and exceed the speed of light. So that's not good. For any given electron, the magnetic moment is very, very small. In this case, something like 9.3 times 10 to the minus 24 amp meter squares. But there are a lot of electrons in a physical object. And if all the moments were aligned, they would combine to make a very large magnetic field. Actually, though, in fact, electrons tend to pair up with moments. So the effect mostly cancels out. Only unpaired electrons contribute. And in most materials, these are randomly arrayed, so the field cancels too. You can see that over here as sort of standard things, and the electrons are essentially randomly distributed. So when you add up all the magnetic fields vectorially, it's kind of zero. But in iron, it can turn out that they all end up lining up together, that they reinforce and pull things to be aligned. This gives the block of iron its own magnetic moment, which is also aligned and has been amplified by those. Still, it's not entirely that simple either. Iron atoms will tend to align in small regions which are called domains. They're about 1/10 of a millimeter across. Within a given domain, most of the atoms will line up in the same direction, and that gives the domain a significant magnetic moment. But the orientation of the domains are still kind of random, so on average there still isn't much field. And we see that illustrated over here. Now we have these things where these little abstractly shaped little regions all have their own moment, but they're not particularly aligned with each other. Within a given domain, all the atoms are more or less aligned. But if you bring a strong enough magnet near a ferromagnetic material, the external field threads through the material. It torques the individual domain moments, remember we talked about that, making it energetically favorable to be aligned. Domains that happen to be aligned grow at the expense of misaligned domains. Eventually, nearly the entire material is made of aligned domains, which point in the same direction as the external field. The material is now said to have an induced magnetic moment. We've run into this word a couple of times, meaning this magnetic moment is because there's something outside orienting it. You might remember we had induced polarity in insulators with electric materials. For paramagnetic materials and for ferromagnetic materials in weak external fields, that's about all that happens. If you take the external field away, then the random thermal motion of the atoms re-scramble the domains, and the induced field disappears. So a paramagnet doesn't tend to have magnetism, but it will in the presence of a magnet nearby. For ferromagnets in strong external fields, though, more subtle changes can occur in the domain structure, and many of the domains remain aligned. They get kind of stuck on defects in the crystalline structure of the material. They can't sort of rotate past these little blockages. That's why ferromagnetic materials can be magnetized and turned into permanent magnets. But anything that delivers a lot of energy to the material, say heating it, or sometimes even just dropping it, will free the domains, will jiggle them around enough so they can randomize, removing the magnetic properties. By the way, it's this alignment that allows you to stick magnets to other magnetic materials. If you take a magnet and bring it near a thing of iron, it will be attracted to the iron because the fields line up together. In other words, if we talk about, we have, your refrigerator, and I bring in preferably a strong magnet with a north and a south, which means that there's magnetic field going like this, then it's going to align all of the little guys in the same directions as that magnetic field, giving them a north and a south, and we can see these north and souths will attract. So the magnet will get stuck to the iron or the steel or whatever. A chain of paper clips is hung from a permanent magnet. Which diagram shows the correct induced pole structure of the paper clips? And our key thing is that the induced structure will line up with the existing magnet. So the existing magnet, remember, is doing something like this, leaving the norths, re-entering in the south. So our induced fields must also point that way. So, and I sort of suggestively picked, it's case B that's going to be our correct one, because in that case the permanent magnet has a field that looks like this, and all the induced fields point in the same direction.